Hello, my name is Eric. I'm pleased to present our work on Modality-Agnostic Attention Fusion for visual search with text feedback on behalf of my colleagues at Yahoo Research, Jack, Simao, and Yang, and our former colleague Kofi, now at Pinterest. The task we're interested in is to retrieve target items from a database containing images of those items, based on a query consisting of an image and a natural language caption describing the difference between the item in the query image and the target item. For this presentation, I'll focus on the Fashion IQ dataset introduced by Guo et al. Last year. They showed pairs of images to annotators and asked them to write short descriptions of the differences between the pictured items. For example, this top in the first row with a green box around it has a cheetah pattern, which distinguishes it from the black top in the query image according to one annotator. Our model's top 3 retrievals for this query include the cheetah print top and a couple items with similar patterns that are not labeled as correct and therefore considered wrong for the recall at k metric. Following previous work on this task, we used standard architectures for initial processing of the image and text inputs, and then we focused on how best to combine the extracted image and text features. The best method we found is pretty simple. We take the sequence output phi-t from the text model, in this case the hidden states of an LSTM, and the sequence phi-x of image features at each spatial location in the image feature maps at the last 2 blocks of a ResNet model. We linearly project the sequence elements from the 2 modalities to the same dimensionality, and then we simply concatenate these projected sequences. The concatenated sequence goes through some transformer self-attention blocks where the sequence elements from the 2 modalities are not distinguished in any way, hence the name Modality-Agnostic Attention Fusion. The equations here show the self-attention computation on the concatenated sequence phi. We then average pool over the output sequence to get the final vector representation, which can be compared by L2 distance to the database vectors. These are obtained in the same way, just without the text input part of the model. In this example, the 6 words "is solid black with no sleeves" give 6 LSTM outputs that are then concatenated with 7 times 7 plus 14 times 14 image vectors to give a sequence of length 7 times 7 plus 14 times 14 plus 6, or 251. Attention layers operate on this concatenated sequence, then we pool over the resulting 251 vectors to get the final representation. The whole thing is trained end-to-end with the batch-based softmax cross-entropy loss. Our method outperforms other single models that came before it and used only the same training data on several existing datasets. We also adapted the datasets birds to words and spot the diff that were designed for the reverse task of generating the difference caption for our retrieval task. And we hope other groups will evaluate their methods on the interesting datasets that result. I glossed over a number of important details when describing our method. This table shows an ablation study confirming that it is best to pool over all the post-attention sequence elements, including those corresponding to the text, but after averaging over each type of element separately. So each resolution of image feature and the text features each get pooled separately, and then those 3 things get pooled together. It is also important that the database images go through the attention blocks, even though they are not being fused with any text. These design choices together account for about a 9% relative improvement over the alternatives. It might seem natural to separate the attention connections by modality, for example, alternating image-image and image-text attention. We hypothesized that the modality-agnostic architecture would better allow the model to learn what interactions are valuable, while using fewer parameters to allow all possibilities than approaches that separate the modalities would. Experiments on Fashion IQ support our hypothesis, as we found that modality-agnostic attention fusion outperformed a broad class of modality-separating alternatives. Additional experiments are reported in our paper. We attempted to visualize what the attention blocks were doing, and we found a surprise that I'll try to explain briefly. We expected from the image captioning literature that a word like sleeves would tend to have strong attention weights to the corresponding regions of the source image. Some attention weights appear to do something like that, but we frequently saw the opposite. Attention weights tending to be small for the corresponding image regions, such as the blue holes around the sleeves in the bottom right attention map here for a particular attention head. Thanks for your attention, and here's the team that worked on this, my email, and the URL for our full-length paper on arXiv.